I'd like to welcome Sam Coogan from Georgia Tech. So he'll speak on probabilistic guarantees for autonomous systems.
All right, thanks a lot. So I'm Sam Coogan. I'm assistant professor at Georgia Tech. My majority appointment's in electrical and computer engineering, but I have a one-third appointment in civil and environmental engineering. So I'm going to tell you a little bit about my lab group. We call ourselves the Formal Methods and Autonomous Control of Transportation Systems group. A lot of my research focuses on transportation as applications, but we also think more generally about robotic and autonomous type systems. So in this upper left corner, if I can get the video to play, so it's a little hard to see, but these are quadcopters flying through hoops in what we call the Robotarium at Georgia Tech. So some of my work focuses on how we can do autonomous control of aerial robots. Down here in the bottom left, this is a simulation environment of autonomous multi-agent systems moving through a city environment. This was a DARPA project where we were trying to do sort of end-to-end building isolation, building rescue mission type work. And so these teams of robots are autonomously figuring out how to break into teams and patrol the environment and achieve certain objectives. In this upper right corner, this is robots, again, on the Robotarium, simulating a roundabout example, a roundabout situation where we have autonomous algorithms to get these robots to navigate the roundabout without collision. And then in the lower right, this is just a video I took now quite a few years ago in LA, showing traffic flow patterns on a freeway and on an arterial road. This is Sunset Boulevard, the 405 in LA. And so we try to study these systems in the context of control and analysis, traffic flow modeling, traffic flow control, these sorts of things. So this is our motivation. Today I won't talk too much about application-specific work, but this is sort of in the background, motivating a lot of the things we're trying to think about. Okay, so let me talk a little bit about modeling a stochastic system. So if you open an undergraduate computer science textbook and you turn to sort of the Markov Decision Process chapter, you would find something like this grid world example. So the idea is you have some autonomous robot, something like this. This is something we actually have driving around in our lab. And the robot, say, has some discrete actions, up, down, left, right. These actions might have probabilistic consequences on where the robot moves. So if you apply the up action, maybe most of the time you move up with 80% probability, but maybe there's a 10% probability you move up and to the left, and a 10% probability you move up to the right. And so you have this robot moving this environment. You have the ability to control the robot, and you might have a control objective that could be fairly complex. Maybe something like visit each blue square infinitely often as you move through the environment, but make sure you never visit a red square, things like this.
And why for a robot you will have a probability?
So, I mean, it could be simply the case that you don't have the motors characterized very well, and so when you apply kind of an open loop up command, maybe it doesn't exactly provide that up command. That could be one reason. There could be something in the environment kind of disturbing the system that you don't have very well modeled. I mean, if this was out in the world, you could have things like road grade and road slope could change exactly where you end up. But yeah, I mean, yeah, this is again sort of a toy example. I guess in a real world you would be measuring this and doing it pretty well. But this is sort of a classic setup for an undergraduate computer science course where they would try to figure out how to control this type of environment. And so this will kind of serve as the foundation for what we're going to try to do in this talk. We'll extend this in several ways. So okay, right. So how would you go about analyzing this system? First, you would abstract this into some sort of finite number of states, right? You would color the states. You would have actions that correspond to probabilities of transitions. And then you could construct a Markov decision process, right? And so this Markov decision process would have a set of states. We can represent them as tuples here for their 4x4 grid. A set of actions that are available to the agent at every state in the system. In this case, maybe there's 4 actions. And then, of course, a transition kernel that tells you how the system evolves. And so it takes in a state, an action in the state, and it provides you the probability, right? So for example, in this example, if you're at position 2,2 and you apply the up action, you'll end up at position 3,3 with 10% probability, right? And And then we typically think of this as a labeled Markov decision process. So the states are labeled with propositions of interest. So in this case, some states might be labeled blue, some states might be labeled red, some states may be unlabeled. And then, of course, the labeling function matches symbols from our set of labels to states like this. Okay? Okay, and then so suppose you have this Markov decision process abstraction of your system, and you're given a goal, something like synthesize a control strategy that maximizes the probability, or maybe the control strategy is fixed, and you want to verify the probability of something like this, reaching a good blue state infinitely often, and encountering a bad or red state finitely many times. This is actually will be an important canonical example, this idea of reaching some states infinitely often while avoiding some states eventually will be a canonical example. But sort of the important thing to notice here is that it's quite straightforward to show two important facts about this particular problem setup. The first is that the optimal controller is memoryless. You don't need to remember anything about the previous state you visited. The optimal controller will just map from current state to action. And the second fact is that maximizing the probability, trying to compute this controller, is pretty easy to do. You would break this up into, you would do first a graph-based search. You would find certain strongly connected components. I'll talk a little bit more about this later in the talk. And then you could do a linear program to compute the maximum probability of reaching these maximally connected components. So it's quite straightforward to solve this control problem or to verify this problem if you're given a controller. So right. So the idea again, this sort of given this sort of specification, given a Markov decision process, not too difficult to reason about its control strategies.
So as an example for the reaching a good blue state, do you mean every good or a single particular one?
Good question. So here we're just going to mean any good state, right? So you could visit this state infinitely often, and that would count as a good trajectory of the system. And likewise, you want to avoid all of the red states eventually.
What is the exact meaning of visiting infinitely often?
So we're thinking of the system evolving forever. So a trajectory is an infinite set of states, and we just want to make sure we want to see in that infinite string, we want to see blue infinitely often. And we want there to be a finite number of red symbols. So eventually you have your final red symbol and it doesn't show up again. That's what we mean by this. I'm going to go ahead.
When that happens, it's not a part of the setup.
Right, yes, it doesn't matter when it happens, that's right. We just want to know, we want to somehow be able to guarantee that eventually we avoid that.
So in a way, you're not interested in the transient action.
That's right, yeah, that's exactly right. So, and that's how this would go, is you would partition this into strongly connected components. You would want to find strongly connected components that are in some sense a sync with blue states, and then you want to make sure that the red states are in transient connected components, and so we'll get to that. But yeah, that's exactly right. And the reason this specification is interesting is I'm going to connect it to this idea of temporal logics that we talked about briefly, and I'll talk about that. But this is sort of the canonical case that shows up in these temporal logics. Okay, so I guess the next slide is temporal logics. Why are we interested in this? So the controls community has gotten increasingly interested in this idea of being able to write down fairly complex specifications for an autonomous robot. And a common formal way of doing this is using something called linear temporal logic, which is a formal syntax for writing complicated expressions that tie sort of Boolean properties about states of the system with temporal operations. So here's three good examples that are sort of written in plain English, but they can be easily translated into sort of a formal sentence written in temporal logic with symbols and things like this. So for example, you want to eventually visit the blue state, but only after you visit a red state at least once. If you ever visit a red state, then you need to visit a blue state within 3 time steps, or never visit 2 blue states in a row, right? These are all specifications that fall within the class of linear temporal logics, which means that we can reason formally about these. And what I'm going to show, or what I'm going to, this is not my result, certainly, but what's well known is that you can take any of these LTL specifications and sort of convert it into this canonical reach-avoid problem that was on the previous slide, which is one of the reasons why these linear temporal logics are so powerful and useful in these contexts.
Does the linear temporal logic involve probabilities too?
So we'll get to this, right? So there's been several attempts to extend temporal logic to a probabilistic framework. We're going to take one particular approach where we put a probability operator on the very outside of these sentences, and so we ask, what's the maximum or minimum probability that we achieve a linear temporal logic specifications? Now, there are other languages that nest probabilities. So you can compute the maximum probability that you eventually reach a red state with a certain minimum probability, and you can kind of nest these. We're not going to go down that path. We're going to just put one probability operator on the very outside of an LTL specification. Yeah.
This temporal is supposed to have time in it, right? So it involves time. So, but in the first triangle, where is time?
It's the eventually. So yeah.
Okay, got it.
Yeah. Good.
But how is that if you involve time, then the system somehow later on is autonomous? You just add a variable to remove time?
So I guess the time doesn't need to explicitly show up in how the controller operates or how the system operates, but the time is in the sense that a trace of this system is going to be an infinite string of symbols, and we want to reason about this whole infinite string of symbols. And these are specifications over that infinite string of symbols. Yeah.
But William, x dot is equal to x, so exponential function.
The
solution depends on time still.
I know how to change it. I know how to change it to autonomous. I mean, you just put a new variable called x or called t, and t prime equals 1. But I'm interested
it's not
in
always
linear temporal logic. How is that done?
And the next variable is not always equivalent thing. Because when you
Well,
add
equivalent in what sense or not?
yeah, because it's not even on leaf thing. If you add a new variables, you have initial conditions and so on. So it's like
Yeah.
going from one to the other. is
That
different.
variable is not a problem. He'll do it all the time.
Okay.
Yeah, but I'm not sure that's what he means by autonomous in this context.
Yeah, so I'm using autonomous in a more, yeah, you're right. So you're using it in
More like
a,
a self-driving car.
yeah.
Right.
I'm using it more, yes, but not in the technical sense, you're right. But thanks, yeah. Although we will get to autonomous discrete-time systems that are autonomous in your precise sense, that's right. Okay, so here's an example. Let me just demonstrate how you can convert one of those specifications on the previous slide to this canonical reach avoid problem. So for example, the specification eventually you reach a blue state, but only after you reach one red state, right? So this sentence can be written in some sort of formal syntax, and if you've ever seen somebody give a talk about temporal logic, sometimes they spend 3 slides going over the syntax, which is not a very useful use of 3 slides. But the idea is that you can take any of these sentences and you can go online, find off-the-shelf conversion toolboxes. You type in the correct string of symbols, and it produces an automaton. This automaton somehow encodes the satisfaction of this specification in a reach avoid type framework. So for example, this sentence eventually reach a blue state, but only after reaching a red state gets converted into this automaton with 4 states. It has a reach condition that you want to get to this state infinitely often. In this particular case, if there are no states that need to be avoided in finite time, but you can kind of see how this would work. So suppose you have a string that's fed into this automaton like this, and so this string should satisfy our specification. We do reach a blue state after we visit a red state. We can look at what's going to happen in this automaton. So first you get fed an empty symbol, you stay in state 1, this is where you started. You get fed another empty symbol, it satisfies this label, it's not blue and it's not red, so it stays in state 1. You see a red symbol, and so you'll execute this edge right here, and you'll go to state 2. And then you'll get another red symbol that's not blue, so you stay in state 2. Then you get an empty symbol that's also not blue, so you stay in state 2, but suddenly you see a blue symbol, you transition to here, and now you stay here forever, that has a 1 on a probability edge, right? So this string, when fed to this automaton, gets to this state, and it stays in the state forever, and so you could use that to certify, yes, this string satisfied this linear temporal logic specification. And the important idea is any temporal logic linear temporal logic specification can be converted to an appropriate automaton like this very easily using kind of off-the-shelf algorithms, right?
So it's the same as finite state machine then?
Yeah, so it's a finite state machine sort of augmented with this acceptance condition that there's a subset of states that need to be visited, right? So when I say finite state automaton, I guess I'm thinking of a finite state machine.
So when you say, so it's kind of just like the terminal states of a finite state machine, right? I mean, you stay there, right?
Yeah, not every automaton is going to have a terminal state sort of so obviously like this. It could be a whole component of the,
Right.
and there could be 4 states that are labeled with this reach condition.
Right.
But any specification will result in an automaton with a reach avoid condition. You want to eventually reach this set of states infinitely often. You want to avoid this other set eventually. And again, the thought is that you feed in an infinite string. So none of this is finite. This thing reads an infinite
It's
string.
what they call the language of the...
Yes, that's right. That's right. So this automaton accepts the language. It's the accepting language is exactly equal to the strings that satisfy this temporal logic specification. Right. Good.
So do you use that theory, like context-free or whatever kind of other thing about grammars and all that?
I mean, so these temporal logics are context-free, and this is what we're using here. Yeah. Good. Okay, so this is just a video. I mean, so in my lab, we can do things like this. So we can have robots running around with temporal logic specifications satisfying this, but this is not really the important part. So let me just kind of move ahead. Okay, so what do I want to focus on today? I want to focus on what happens when you have agents like this, where instead of having exact probabilities on the edges, you have a range of probabilities, right? So now maybe you have a collection of robots. Each robot itself has sort of uncertainty in the motor encoders, but you don't even know which robot you got, right? So now when you apply an up action, you get a range of probabilities that could possibly happen when you apply that. So maybe you have a particularly reliable robot, and every time you apply the up action on this robot, you actually achieve the up transition, but you get 0 here, right? And so you have something like this, and we'll see in a few slides why we're interested in this. These arise in the way we're going to solve certain problems, but let's just kind of write down a formal model for what this would be. You can find these in the literature. They're called bounded-parameter Markov Decision Processes, and they look almost exactly like a Markov decision process, except for now you have 2 transition functions. You have a lower transition function and an upper transition function that give you the lower and the upper transitions on each of these edges. And of course, they have to satisfy some reasonable properties, like the lower needs to be less than the upper for every possible transition. And if you sum up all the lower transitions, you need to get something smaller than 1. And if you sum up all the upper transitions, you need to get something greater than 1, right? So if you have sort of this tuple, this object, we would call it a bounded-parameter Markov decision process. And you can still ask all of these same questions. How would you control this? How would you verify a controller for this type of system? And so that's what we're going to be focused on in the remainder of this talk. Okay, so we're going to answer 3 specific questions. The first one's going to be, what happens if you have a dynamic system with some uncountable state space, like Rn? And the answer is going to be, we're going to take that state space, we're going to partition it into regions, and then we're going to create a bounded Markov decision process abstraction of that. And so that's where these bounded parameter Markov decision processes come from in our world. Then we're going to talk about what happens when you try to solve these simple reach avoid problems in a BMDP. And the answer is it gets much more complicated, and it really gets much more complicated for one specific reason. If you have an edge in your BMDP where the lower transition probability is 0, but the upper transition probability is non-zero, then you don't know if that edge actually exists. And so when you try to do this process of finding strongly connected components, you can't do that you have to be very careful about how you do that, because these edges may or may not exist in the system that the actual underlying system. And then we'll talk briefly about how we would solve against more complex specifications. And again, it's basically the same idea. We can reduce this to a reachability problem using these automata for temporal logics. And then I'll talk about refining the state space. So we start with a partition, and I'll talk a little bit about how we further partition to get what we're after in this context.
But when you say the reachability, are you just looking at it as a graph problem?
Right. So once we get to this abstraction, the reach avoid problem, right. So when I say simple reachability, I guess I mean we can reduce it to this reach avoid problem. There's a subset of the state space where we want to reach infinitely often, another subset where we want to eventually avoid forever. Yeah, that's right. Okay, so this is ultimately going to be the types of systems we're interested in. So discrete time systems with a state x that gets updated through some potentially nonlinear update map f, and then this vector w will be the random disturbance that enters into our system, and this random disturbance has some probability density function on it. So in fact, for the rest of the talk, I'm actually going to turn this conversation into a verification problem. So we're going to assume somebody's provided a control strategy, and then we're going to talk about verifying that control strategy. But I'll talk a little bit about what happens if you have control inputs. And then here the state space is Rn or some subset of Rn, which means that we can't, of course, directly compute some sort of finite bound Markov decision process, which means we need to do this sort of partitioning approach that I'm going to mention. So this is where we're going to start, and then I'm actually going to specialize slightly more to a specific form for this to get some computationally tractable algorithms for this problem.
And the reason it is Rn rather than Cn is because it's just that's all that is needed, or there is something Rn is something specific about Rn.
Because control theorists rarely think about Cn, I guess. I don't know. It's an interesting question. We're going to do some of the techniques, I guess. We're going to specialize this, and we'll think quite specifically about Rn. But I don't know how quickly this generalizes. Yeah, it's a good question. Yeah. Okay, so again, we have an update map. We have this dynamical system. It's discrete time. You initialize somewhere in the state space, and you get a random walk on your domain, right?
And,
yeah, sorry.
And is it actually when you calculate? Is it Rn or it's Qn?
So I'm not a computer scientist either, so I don't care about the Q. But these are all valid questions from a computational perspective. But for the algorithms I'm going to develop, I'm just going to assume we can actually deal with real numbers. Yeah.
Okay.
Yeah. Good. Okay. So of course this is a random walk. And suppose you have some sort of target set in the state space, and you have some sort of probability threshold. And you'd like to color the domain D with some green states and some red states, and you want to color them. You want to color you want to color parts of D where the probability that this trajectory reaches T, if it's greater than the probability threshold, you want to color it green, and any other states you want to color red. So this is our goal, right? We want to take this state space and color it red or green. Of course, there's randomness here, so if you initialize in the same spot, sometimes you might hit the target, sometimes you might not, which is why we have a probability threshold. And so this might be something you're looking for, right? In principle, the space can be divided into red and green exactly, and you want to find this division, right? So this will be what we're after. So here's the approach we're going to advocate for this. We're going to suggest that you take your state space and your targets. You partition the state space into what we're going to use rectangles for particular computational reasons. So you partition the state space, and now you want to color every partition of the state space with one either red or green. But we're going to have to introduce sort of this unknown yellow color if we can't say for sure whether the probability is greater or lower than the threshold, right? So this might be the result of this coloring process. And when we have yellow regions, it means that there are some states within this yellow region where the probability is lower than the threshold and they should be colored red, and there are some states where it's greater than the threshold so that we should color them green, but because we only have one color per partition, we can't do that, so we're going to color it yellow. And then of course the natural idea is perhaps you can chop these partitions up further and color them further, and we'll talk a little bit about that towards the end.
And so this is the steps, these triangles.
Yeah.
It's just a big picture of how the procedure works, or it's actually something for complicated algorithm, or it's something obvious. So what is partition the state space?
So I think this is sort of obvious. I mean, I think a lot of people do this approach. What I'm going to talk about is kind of how we do this in a computationally useful way for certain class of systems, I guess, I suppose. Right, yeah. The idea of taking the system and partitioning it is sort of the bedrock of a lot of these formal methods, techniques, and controls. In the probability context, coloring them like this is also sort of interesting. Yeah. Good. Okay, so the idea that we're going to propose is to take the system, partition it, and then compute a bounded parameter Markov decision process abstraction, right? And what you want is to compute lower transition bounds and upper transition bounds, and ideally the lower transition bound should sort of be the minimum probability from any two states. So So suppose we now have this abstracted. We want to compute the lower and upper transition probabilities from one discrete state to another discrete state. Ideally, we want the lower transition bound to be sort of the minimum probability that our update equation f lands in q prime, given some q naught within that original state, and we want to compute an upper transition probability that is this maximum, right?
So that partitioning,
yeah.
Does it depend on f?
So you should. So different people have different philosophies on this. The approach we take is we start with a partition, we color, and then we're going to refine the colors we're going to refine the partitions based on this coloring, and in that sense, the refinement becomes tied to F. Does that make sense? But in principle, you can choose any partition and do this coloring scheme independent of. I mean, of course, F tells you which color to color it, but the partition can be given to you independent of F, right?
And are there initial conditions involved?
No, so we don't think of this. We don't really think of initial conditions here. So any state is colored. Okay, you can either think of it as no initial conditions, or at any given state, we're considering that to be the initial condition. And that's sort of the idea. So this is what we would be after. We're actually going to be happy if we can compute sort of a lower approximate of this and an upper approximate of this. It might be a little conservative, but it'll work for our purposes, right? Right. Okay. So I guess I just had some more pictures, right? So you want to kind of search over all possible initial conditions x naught in state q and consider any possible transition to a state q prime. Good. Okay. So then we have a definition. So this is a definition of what it means to be a BMDP abstraction of this system. We'll say that a partition q with a transition function, with a lower transition function and an upper transition function, is a BMDP abstraction of our nonlinear system. And here I'm already writing this in a particular form that I'm going to introduce on the next slide. If for any two states q and q prime, you have this this inequality satisfied, right? So these lower transition probabilities under approximate the true lower transition probability, and the upper transition function over approximates the true over approximating transition. And so the philosophy here is that a BMDP abstraction somehow over approximates the true dynamics that are underlying the system. And because it's an over approximation, that means that any algorithms we get to color the state space, they're going to be sound in the sense that if we color a state green, it means we're confident that it's green, but it's conservative in the sense that we're going to end up with some yellow states that we can't color. Good. Okay, so let me talk about a class of systems that we've been studying for a while where we can actually do this in sort of a computationally efficient way. So we're going to specialize to something that looks like this, where we have a nonlinear update and then an additive disturbance added to each component. We're going to assume f is something called a mixed monotone function. I'll define that on the next slide. And then we're going to make, to be honest, a fairly restrictive assumption on the disturbance, but it allows us to have a computationally efficient techniques here. We're going to assume that every element of W, this disturbance vector, is drawn from a symmetric unimodal distribution. So there's a disturbance, a probability, uncertainty hitting every channel independently with some symmetric unimodal probability distribution. Okay, so let me tell you a little bit about these mixed monotone systems that we've found to be quite useful in a number of contexts. So let's, for a moment, forget about the probability, the disturbance input, and let's just think about a map x prime equal to f of x. This system is defined to be mixed monotone if you can satisfy these three properties. If you can find a decomposition function, that satisfies these three properties. This decomposition function takes in two vectors, it returns one vector, and you need to satisfy three properties. The first is that if you give the decomposition function g two copies of the same vector, it returns f evaluated at that vector. So in some sense, this decomposition function contains all of the information about your nonlinear dynamics. And the second is it needs to have these sort of monotone properties. If you fix the second argument and you choose an ordering, if you choose two first arguments that are ordered with respect to each other, and here I'm thinking of ordering to be component-wise ordering. I literally mean that every component's ordered. You can generalize this to arbitrary cones at certain expense, but it's typical to think of this and component-wise, and then it ties naturally to our rectangles. And you need the decomposition function to be ordered after you compute, after you evaluate these ordered first arguments. And then you also have an ordering relationship, but it's reversed for the second argument. If you choose y1 less than y2, you end up with g evaluated at y2 being less than g evaluated at y1. This is called a decomposition function. It generalizes this idea of a monotone dynamical system, where really, if you kind of go to familiar theory out of people like Hirsch and Smith, for monotone dynamical systems, it's equivalent to sort of thinking of a decomposition function that just happens to be equal to your original update map. And so you have sort of this first relationship but not the second relationship. So this mixed monotonicity allows you to generalize this idea and have a little bit more structure. Okay, so mixed monotone systems are important for two reasons. First of all, they actually are quite a general class of systems, and we do see them a lot. We first encountered them studying traffic flow networks, which is where we got interested in them. And but they show up quite a bit in applications, certainly more general than just monotone systems. But the other reason we like them a lot for these ideas of formal methods type applications is that we can over-approximate the one-step reachable set very efficiently from these mixed monotone systems. For example, if you think of a rectangle with a lower corner x1 and an upper corner x2, and you want to know all of the possible states that you could hit after taking one of these vectors through the update map f, it's going to be contained in a rectangle whose lower corner is defined by the decomposition function evaluated at x1, x2, and then the decomposition function again evaluated with the arguments reversed. Right? So again, it's an over-approximation, but the idea is it's very efficient. You give me a rectangle defined by a lower and an upper corner. I can compute 2 points, a lower corner for my decomposition function and an upper corner for my decomposition function. And it's guaranteed to contain the true reachable set, which could be something complicated and not worth figuring out on its own. And of course, this generalizes to arbitrary dimension. This is still one function evaluation here. So this, if you think of this as an matrix multiply operations, it's, I guess, linear in the dimension as opposed to being exponential, right? So if you were trying to use like polytope reachability methods for a linear system, you would have to still compute all of these corners, right? Here we just do it with 2 extreme corners, and it applies to nonlinear systems so long as we can find this decomposition function.
Questions. So first of all, this is where you use real numbers, right? Not complex numbers.
That's right. Yeah. So this would be the thing that would be, I don't know how it would generate to generalize to the complex.
And how decidable is the monotone property?
Yeah. So that's
How is it decidable in practice? Like how practical decidable? So do you prove a theorem for each function? So somebody gives you a function, you sit down and try to prove it, or there is something more standard?
Okay. So one, I can't remember. I have a slide on this. I do. So let me answer that in a couple ways. Let me begin by a special case that's easy to check.
So you have some sufficient conditions.
Yes, this is a sufficient condition. This is a pretty easy sufficient condition to.
Excuse me.
Yes.
Can you go back to the previous slide?
Yes, of course.
The last one there, you should, it's your gxy equals x, fx for
Yes.
all y.
So,
Or not
yeah,
just
so
y.
what is this bullet trying to say? It's trying to say that you can recover the definition of monotone dynamical systems if you simply, if choosing G to be equal to F satisfies these conditions, then you would recover a monotone.
Oh, independent of.
Yeah, right. So this is exactly right. So monotone systems are sort of a special case where you don't care about the Y. That's right.
So f of that's
Literally, fx automatically monotone already.
That's right. Yes, it's exactly right. Yep.
So f is a constant, then it's monotone, right?
Yes.
If f is degree one polynomial, is it it's monotone, right?
Right.
Ax plus b.
Yes. So then it's not necessarily monotone, but it is guaranteed to be mixed monotone.
Mixed monotone. Okay. So
Yeah. Yep.
How about degree 2 polynomial?
Okay. So let me get to the special. So let me do this special case on the next slide, and then I'll.
Okay.
Yeah. So here's the special case that you can use to check if you have a mixed monotone system. So and this generalizes. Okay. So if you wanted to check if you had a monotone system, you would take f, you would compute its partial derivatives, you would get its Jacobian matrix, and you would look and see if every entry of the Jacobian was positive. And if it was, you have a discrete-time monotone system. What we can do here is we can generalize this idea. Now it's just a sufficient condition. In the monotone case, it's necessary and sufficient. In this mixed monotone case, it's just a sufficient condition. But if you compute this Jacobian, if you look at every entry of the Jacobian matrix f partial with respect to x, and either entry is either uniformly positive over the whole state space or uniformly negative over the whole state space, then the system is mixed monotone, and you can construct a decomposition function in the following way. The ith entry of the decomposition function is equal to the ith entry of your update map f, except anywhere where you had a negative relationship in the partial derivative, you strike out xj and you put in yj. And then you just concatenate to get your decomposition function g. And it's easy to check. I mean, of course, this requires f to be differentiable, but if you have that property, it's easy to check that you satisfy these three conditions, which are sufficient for the conditions on the previous slide. So, and in fact, you can even generalize this to functions that have bounded Jacobian. If I can give you bounds on the Jacobian, then I can sort of cleverly choose offsets to get a decomposition function. And so the message here, and I think this partially answers your question, is this idea of mixed monotonicity is actually quite general. So simply asking the question, can I find a decomposition function for this system so that I can show that it's mixed monotone, it's actually quite a general property. What's going to happen is its usefulness as a tool for doing reachability computations is closely tied to how good of a decomposition function you find. And so what happens in practice is you look at your system, you sort of use some physical intuition, and you dream up kind of a particularly appropriate decomposition function, which gives you tight bounds, basically, from that previous slide.
So G is a lot not unique.
Right. That's right. Yeah. Right. Yeah. And that's sort of what we're finding in practice. I mean, and not just our group, and other groups that start thinking about this, is again, there are plenty of systems where you can find. Okay, if you happen to satisfy this Jacobian condition where you have constant signs structure in the Jacobian, then when you compute this rectangle, it's tight. You know it's the tightest rectangle that contains the true reachable set. If you don't satisfy that Jacobian condition and you're finding your decomposition function using some other method, this may not even be tight. And so this could be a very bad approximation of your reachable set. It's still a valid approximation. You can still apply the theory I'm going to show in the next few slides, but it may not be very useful.
And f of x equals x squared. Is it mixed monotone? Yes, you can compute a decomposition function that would correctly handle the two. Yes. Yeah, you could compute a decomposition function. So what is the simplest example of not mixed monotone? That's polynomial. Simplest polynomial that is not mixed monotone. Polynomial and one variable.
And one variable,
Always.
Always mixed monotone.
Yeah, I think so.
Yeah, with one variable, it might be hard to come up with interesting examples.
Because I mean, polynomial graphs are like that, right? So all the points that have positive is one region, and also, you take the derivative of that, it's still a polynomial. So it's either positive or negative, right? So you have that to satisfy that condition for mixed mono. No? I'm guessing, of course.
Yes, you could do, right, so you could...
It's fixed, right? So
you take the derivative of the polynomial, it's a polynomial. The graph is above the x-axis or below. So the points that are above is one region, and the other one is the other.
Right.
Is that right? I mean, that's how we partition,
Yes,
actually.
yeah.
That's how we partition the real line.
So the D.
The delta ij's. The delta
No,
ij.
I mean D, big D. D, is it fixed? It's
D is just some interval in
So in your case, so D would be fixed. It's the domain. So in your case, it's an interval.
Right.
And you're trying to over-approximate kind of the map of an interval by kind of decomposing this function. And so you would have to match up, I guess, the positive negative components. Right. Yeah. That's a good question. I mean, this is not so interesting in a scalar case, right? But I should think,
in practical applications, so how frequently f is not polynomial?
Rarely, I suppose.
It's typically a polynomial.
Yes, in the examples we look at, that's right.
Typically multivariate polynomial.
It's multivariable though, that's right.
Multivariable polynomial.
Yeah. And again, this sufficient condition. I mean, a common question might be, how does this look for a linear system, right? X plus equals a times x, right? All you do is you take your A matrix and this slide tells you to decompose it into the positive entries and the negative entries, and now your decomposition function is kind of this A positive times x plus this A minus times Y. Let's say A negative times Y, right? And that's how you would decompose a linear system. So any linear system it satisfies this condition and is immediately mixed monotone. And what that means is, right, so if you think about taking a rectangular set and mapping it through a linear transform, you're going to get some polytope on the other side, right? And so this tells us we can over-approximate that polytope by computing some extreme corners using the decomposition function, basically. Yeah. Good. Okay, so then the idea here is that we can use, okay, if we have a map where F is mixed monotone and we have this additive disturbance vector. That was strange. Okay.
Maybe some loose connection.
Is it? Maybe not. Okay.
Yeah, it's working. It's working.
Okay. I won't touch anything. Okay. Right. Okay. So the idea is that if F is mixed monotone, we can sort of use this idea of over-approximating reachable sets, and then we can use the fact that the disturbance vector is hitting every channel independently to kind of reason about this. So here's the cartoon picture how you would do this. Suppose you're trying to compute the lower and upper transition bounds from a state from rectangle Q to rectangle Q prime. You first would define, this rectangle is defined by a lower corner and upper corner. You would use the mixed monotone property to compute an over-approximation of f of x, right? So maybe that gives you something like this. And now, because of this particular, because we're assuming this very particular structure on this stochastic system, the disturbance vector now hits the system along each component separately, right? And so what we can think about is we can think about the PDF for the first disturbance sort of sliding along any direction here, the PDF for the second disturbance sliding along any direction here. And now we want to compute sort of the best case and the worst case kind of positions of these PDFs that would maximize, respectively minimize, the transition probability, right? And so if you're thinking about maximizing the transition probability, your objective is to slide these disturbances as close to the center point as possible. And so it's easy to see that it's either going to be in the middle or on one of the two extreme edges. So in the W1 direction, it's in the middle, and the W2 direction, it's as far up as you can go. And then if you're trying to minimize, you independently slide every PDF as far as you can away from the center. In this case, it would be something like this, right? And so you can do this quite straightforwardly for each of these transitions, right?
All these are IIDs, you're saying?
Yeah, so this is the assumption, right? So we're relying heavily on these assumptions. If you tell me that these are correlated or something like this, then it becomes much more difficult. But yeah, that's exactly right. And we're assuming that the PDFs are symmetric. That's another kind of important key assumption, and that it's unimodal and things like this. So I admit that there's somewhat strong assumptions, but that's what we're using here. And then, of course, it's straightforward. So this would be the theorem. So you can compute, given a partition Q, if you can compute these upper and lower transition bounds by basically cleverly sliding around the PDFs for the maximum case and for the minimum case, and then computing some integrals, right? So that's the theory here. And then the output you get is you get a bounded parameter Markov decision process that approximates the dynamic sphere system.
The John distribution will be they're independent, you're saying, right?
Yeah, they're independent. And if they're joint, then it's much, right? Because what happens here is if you have a joint probability distribution, you have to think about sliding it around in this rectangle to maximize the overlap here, and it's not so obvious, right? So maybe in some cases it would be obvious, but in other cases it's not so obvious, yeah. Okay, so back to these reach avoid problems. Let's see how we can type. Okay, so suppose you're given a Markov chain with some states Q. Again, you have these bad states, like these red states B. You have some good states G. And again, you want to find the probability of reaching a good blue state infinitely often while encountering a bad state finitely many times. So here would be the standard approach that you can find in sort of an undergraduate textbook on this. You would take your Markov decision process, in this case, it's just a Markov chain, no control action. So then you would partition it into strongly connected components, right? These strongly connected components, some will have blue states in them, some will have blue and red, some will have just red, and some will have none. Some of these are bottom strongly connected components, meaning that they're sinks in sort of the condensation graph. and you just want to compute the probability of reaching an accepting bottom strongly connected component, and you call the bottom strongly connected component is accepting if it contains at least one blue state and no red states, right? And so you just want to know the probability that you kind of fall into these good strongly connected components, right? And you can also define a winning component to be any state whose probability of reaching an accepting BSCC is 1, right? And so we'll use these ideas of strongly connected components and winning components to reason about these bounded parameter Markov decision processes. Okay, so yeah, so this is the only accepting BSCC in this particular case, right? So here's another BSCC, but it's not accepting. It doesn't have red states, but it doesn't have any blue states, so it doesn't work for us. Okay, so again, the basic observation here is that this idea, it's difficult to generalize. You have to be careful about generalizing it to a bounded parameter Markov chain, simply because when you have edges with lower bound equal to 0, they affect the qualitative behavior of the underlying graph. So here's an example of a BMDP with these intervals, right? And so this BMDP could give rise to here's two examples of Markov chains that would be correct interpretations of this BMDP, but they have very different accepting conditions. Here, because there's a lower bound of 0 on these transition edges, one interpretation is to cut them off, in which case you have a nice accepting component here. But down here, another instantiation would put probabilities on these edges, and then now you don't have an accepting component, right? So again, the observation, and in practice, if we're using this abstraction technique on a nonlinear stochastic system, a lot of times we will get lower bounds that are 0, upper bounds that are non-zero. So this is a practically difficult problem for us. So this is work largely from my graduate student who has kind of very carefully thought about how you should reason about these sort of unknown edges, which he draws with dotted lines on the previous slide here. I guess they're not showing up as dotted lines, but he's shown that we can compute these lower and upper bounds on the reach avoid problem by computing sort of best case largest winning components and sort of worst case largest losing components, right? So I'm not going to go over kind of the nitty-gritty details here. But what he's shown is that in any BMDP, you can sort of independently turn on edges and get sort of your best case winning components. Then you can independently turn off edges and get your worst case losing components. And then you can use those two sort of extreme decompositions to compute upper and lower bounds on these winning probabilities. And then I just want to make a comment about, so then in that process, you have a very good idea of which states are affecting your strongly connected components the most. And so, so an observation he has made is that, let's say you have a partition here, like this, and you've colored a couple states red, some states blue, but you have these yellow states. And of course, the natural idea is to take a yellow state and cut it in half so that you can further color it. And the observation we've made is that it's very important to refine this intelligently. You don't want to just pick up a random yellow state, cut it in half, because it may be a very bad choice. And so my grad student has spent a lot of time thinking about this, and he's presented a heuristic algorithm. So granted, it's just heuristic, but it's tied to the underlying strongly connected components in the graph, and he can assign scores to states based on sort of the most help they could provide to you in resolving some of the ambiguity you have in your decision process. Sort of an interesting point that's come out of this work is that sometimes in order to improve coloring of a yellow state, you might need to refine either a red state or a green state, because this may be yellow because it's going through a path that gets you to certain places, right? And so it's very, and again, I guess just to say it again, to refine this intelligently, it's very important to think about kind of the underlying strongly connected components.
How complicated are these yellow regions? For example, could the actual partition inside this unknown region be divided by a Peano curve?
We don't know much about the complexity. This algorithm certainly doesn't necessarily terminate, right? So you certainly, we don't know that we can get down to a rectangular partition of these green and red states, but yes, yeah.
I mean, how complicated do you allow
Yeah, I don't know. We don't have insights into that. That's a good point. Yeah. Yeah. So we haven't asked questions about the decidability of these problems and when we can kind of really get clean partitions in the red.
So you have conditions where you know it could be partition. I mean, it could be refined nicely.
No.
Finally.
No, we don't. No. So these are interesting questions, but we don't have answers to these questions. That's right. Okay, so let me just kind of wrap up with an example. So this is an example. This is actually kind of coming from a biological example of a bistable switch. We've converted it to this kind of to a discrete time form, and then we've more or less artificially added some Gaussian, some noise terms into each channel. And sort of just for simplicity, we're going to assume they're truncated Gaussians, and so they have finite support. But really, again, they could be any distribution that's symmetric unimodal, and they just have to be independent, right? We will consider two different specifications. So the first is that there's at least an 80% chance of, and I'll show the graph in the next slide, but of remaining in some sort of A region of the state space for 2 time steps before you enter, I think this should be B. Sorry, for 2 time steps after, this is right. There's at least an 80% chance if you enter one of these A regions of the state space that you stay there for 2 more time steps after you enter it. And the second specification will consider that you have less than a 90% chance of reaching some B region of the state space. I don't know, you can read it. So it's something like this, right? And so again, the idea, these can be formally converted into these temporal logic specifications like this, with this string of symbols, and then they can be converted into these automata, and then we can use them to kind of solve these canonical reach avoid problems. So let me just kind of show the result of this algorithm. So suppose, again, in this case, that's at least an 80% chance of remaining in an A state for 2 time steps. So here are your A states are labeled like this. This is, let's say, an original partition of your state space. So we start with a very coarse partitioning. If you were to color based on this partition, using the algorithm I just discussed, you would get something that looks like this. And then if you use this refinement process, you can get something that looks like this, right? And so, of course, you're still going to have these bands of yellow that separate red and greens, and these are the things you're trying to get higher resolution on. But we can color quite fast. Well, I shouldn't say quite fast, but we can do this process and get these kind of colorings for these kind of complex specifications.
So you're using a particular criteria to do the refinement.
That's exactly right. That's an important point that I like to highlight about this particular approach, is that our refinement is specification driven. We're refining based, of course, on the dynamics, but also on the particular specification that we're interested in. Other works, they advocate being specification agnostic, which can be useful, but if you're just refining this blindly, you don't know, I mean, you don't know that you don't want to refine this region, right? So let me make that point kind of explicit. Here's a different specification, very different kind of initial coloring, and we end up with a very different partitioning scheme based on this specification, right? And this is what we're getting out for something like this. Right, again, so I consider it an advantage of our approach that we're specification guided, because it saves you a lot. I mean, you don't partition things you don't care about, right? You really, and you can see it here, you're really focusing on partitioning parts of the state space that will impact whether or not you're a red state or a green state. But nonetheless, even with this approach, we still, even after several refinement steps that, to be honest, takes hours, we still end up with these kind of big yellow bands where we don't know whether or not the states in these regions satisfy this specification. Okay, so just a couple concluding thoughts. So I think that the first observation I want to make is that when you're thinking about these problems in a probabilistic setting, and you're thinking about these sort of finite abstractions, which are common in these formal methods approaches, bounded Markov decision processes are, in a lot of ways, a very good formalism for thinking about these things, putting bounds on the transition probabilities and trying to reason about them. But they do introduce new challenges that are hard to find in literature and haven't really been fully explored. Like, how do you compute these abstractions? How do you reason about the abstractions after you have them? How do you refine them? And so we've made progress in this talk thinking about that. And then the third bullet is simply that if you want to think about what happens when you have a control input, we have some work on that, and we're making progress on that. But in particular, when you have an input that can live in, say, again, some rectangle or some other arbitrary set in RM, you also have to think about essentially refining your input space and thinking cleverly about that. And here's some places where you can find this. So we originally sort of advocated mixed monotonicity for finite state abstraction in this paper. in 2015, and then this was with my PhD advisor, and then my graduate student Max has been working on these BMDP approaches for probabilistic systems for some time now. So thank you very much.
Thank you. Third question. So that variable k.
Yeah.
So what does it represent when you model traffic flow?
It's just the time step.
Time step.
Yeah.
And if it is modeling traffic flow, why not to make it continuous time?
Yeah. So I mean, so a lot of times continuous time is right. I mean, so we do other things where we model this in continuous time. I mean, the problem is if you want to do a formal methods, these sort of like finite abstraction-based approaches, you have to find some way to partition time. Different people do it differently. Here we're just assuming we just sort of just choose discrete time points. But you could try to do something much more. You could try to do some sort of more intelligent partitioning of time and things like this. We haven't thought too much about this, but other people have.
I think when you, I mean, in terms of reality, discrete time is better because in order to compute the next step, you need some time. You can continuously update it, right? I mean, because the computer needs some time to compute the next step, the next state.
But you know, it's
so I mean,
you're talking about maybe solving or like walking through the solution.
No, I'm actually saying the robot. So the robot has to work on discrete time.
Oh, but for example, in traffic control, I think
you can't continuously do it because you need to compute it.
But the point would be to install, so maybe to install road signs and other things correctly. So it's not that you're continuously computing as things.
But that has nothing to do with it. The road signs has nothing to do with it. The road sign will be just part of the specific of the system. You don't change it. You don't change your road sign continuously.
No, but to. So suppose road signs form initial conditions. I don't know, it's something about the system. Or they get involved in some variables. But in the end, you make a decision, maybe you put different road signs. Okay? But the point is that...
that's a totally different problem. That has nothing to do with this autonomous thing. It has to do with optimizing certain things.
Is this correct answer or like...
So I mean, so we certainly do, in other contexts, we think about controlling traffic networks in continuous time. I guess the difficulty is if you're trying to do this against fairly complex specifications, like temporal logic specifications here, reasoning in continuous time sort of introduces a whole new set of tools you need just to sort of reason, what does it mean to have a temporal logic specification over continuous time? People do it, and there are plenty of people that write papers about this, right? But it introduces a whole new set of difficulties as well, right? So in some sense, solving this in discrete time is in these probabilistic contexts first is a good useful step, and then moving on to continuous time. So I would argue that we would be interested in understanding the continuous time formulation. Just from our perspective, it gets even more complicated, and so we're just trying to look at it from certain directions first. So
it's more complicated. We see from the algebra perspective.
Yeah.
Sometimes it's simpler.
That's right, and in some of the
it's a theoretical model, yes.
And
as a practical thing, no.
Yeah. And in some of the other work we do, where we study traffic flow networks and we try to understand things like their stability properties and trying to compute Lyapunov functions for them and things like this, the continuous time is the better way to think about it. But from more of these sort of computational perspectives, it just introduces a whole new kind of slew of difficulties that would need to be overcome.
Mm-hmm.
Yeah.
And the treatment of continuous time systems, it won't be reducing to discrete time. It will be something else, correct?
That's right. I mean, yeah, that's right.
Yeah. And so on. Okay, so okay. Other questions? All right, thank you.
Thank you.